What? Yeah, it's already posted. The thing's posted online. I haven't really advertised the design yet, but yeah, I'll get more details in a second. Okay, so let's get started. Again, this is our brand new unit here. There were some questions about like what exactly the connections will be with the previous unit. So again, the idea is we're still using Newton's laws of motion. We're still going to talk about Newton's first, second, and third law. What we're adding is new forces, right? So we're going to start off by going in some detail about weight and gravity. We're going to do the lab on Friday and activity Monday about spring forces, right? Then we're going to talk about friction as a force, and then we're going to do why things travel in circles. So it really is like a continuation, right? We could have done this as like one big unit, right? That's an option, but I think it makes more sense to split them up. First, do the laws, and then use those laws by studying this motion. So that's the connection there. So let me just get some quick comments about this do now. So Vicky, in your own words, what is mass? What would you say? What comes to mind when you see the word mass? Okay, so something that you would measure on a scale. Lauren, what about when you see the word weight? What comes to mind when you see the word weight? Okay, so then something that is heavy, right, might have more weight, right? So one of the things that you'll definitely, as you started to notice, is in our everyday lives, we might use mass and weight interchangeably, right? They're synonyms for everyday purposes, but they're not synonyms for physics purposes. So we're gonna go through specifically the differences between them. Then I've got 2 Plicker questions set up. And then if there's time, I'm just gonna do a quick little diagram that'll help with the upcoming homework. But if we don't have time for that, I'll record that as a separate video and post that online, okay? So we're gonna start off with, again, we're talking about the difference between weight and mass. So we've got mass, which I'm saying is an intrinsic property. Natalie, have you heard the word intrinsic before? No. All right, looking at the word intrinsic, what do you think it might mean? All right, so something to do with inside. Vicky, what do you think, what does intrinsic mean? There's some amount of independence in it. The idea of in science, natural, okay. The idea of an intrinsic property is it's something about that object that doesn't change, okay? So no matter what I do with the mass, I have this object, it has a mass, that property doesn't change. It's intrinsic. It's like inside, it's internal, right? You might have like an intrinsic interest in something. It's like something inside of you, something that you like. So just a fancy bonus VTOD for the day. Mass is a scalar quantity. Orlandriana, what does it mean that mass is a scalar quantity? What is a scalar?
Doesn't it only have, it has its magnitude?
Yeah, so scalar quantities just have magnitude. The other thing that's interesting about mass is it can't be negative, right? It's a scalar quantity, so that means magnitude only. There's no direction. It's not 5 kilograms north, right? That doesn't make sense because it's a scalar, it just has magnitude. Definition you might give is that it's a measure of an object's inertia. Aji, what is inertia? Yeah. Who can answer Aji's question about what inertia is? Raya, what's inertia? Yeah. So there's that relationship between mass and acceleration. If you have more inertia, you accelerate less with the same force. So Inertia is an object's tendency to oppose changes in its motion, right? And it turns out, and this didn't have to be the case, that the mass of something and its inertia are synonyms. It didn't have to be that way, right? And this was an observation that Newton made. The other thing you'll sometimes hear mass is that it is, the other thing that you might hear is that it's how much matter there is, right? That might be a definition of mass you've heard before, like in a physical science class or in your chemistry class. It's the amount of matter that there is. We'll come back to that in our last unit and talk about mass in another kind of way. Now let's think about which, if any of these situations, would change an object's mass. So would an object's mass change if it's moving? Crystal, what do you think? All right, it would not. What about if it was accelerating, Caitlin? Yeah, would that change its mass? No. And what about if we moved it to another planet? Trinity, would that change the mass? No, it wouldn't, right? That is part of this intrinsic part of the property. So whether it was moving, accelerating, or brought to another planet, the mass stays the same. So would an object's mass change? No. That's what makes mass the mass. Right? There were some of those questions on the last test about how could you change an object's inertia, and the only right answer were the ones where you changed the mass. It didn't matter if it was accelerating or you pushed on it for longer or any of that. The only way to make it have more mass is to make it have more stuff, right? So here, a 10 kilogram mass. All right, now weight, we're gonna need to contrast weight with mass. So weight is a force. If weight is a force, what kind of quantity is it? It would be a vector. All right. Melissa, what does it mean that it is a vector? It has direction and magnitude. So for the most part, we say, all right, so the magnitude of the weight is m times g. Okay, we've already written that down on our free body diagrams before. So this weight, on the reference table, it says Fg. We were calling it W. They're interchangeable. And the direction of weight, I forgot to put it up here, it is always down, right? And in many ways, and I'm gonna share a video on Google Classroom. It's like the first half is what will really, you'll be able to understand so far. But in many ways, this is what defines what down is, right? Down is the direction that gravity pulls you, right? So what's down for us is a different direction what like down is for Australia, right? Because down is pointed towards the center of the earth. And on Tuesday, we'll talk more about why that is. Depending on where you are, down is wherever things fall to because they have weight. Because the earth is pulling them down, right? Like I said, we're gonna go into that next week. But we would say, it always points down. Now, would an object's weight change if it's moving? Remy, what do you think? Would an object's weight change if it's moving? No, it's always m times g. It always points down. Lucera, what about if it's accelerating? No, right? It's pointed down, and it's still m times g. What about if we moved it to another planet? Lauren, what do you think? Yeah, it would, okay? So we're gonna do, the two questions we're gonna do today are about that. What part of the formula do you think changes? Araya, which part of this formula changes when we move to another planet? Yeah, the g would. So we've been calling g the acceleration due to gravity. But it turns out that G, yes, depends on where you're located, okay? So we'll look at an example in a second, right? And in many ways, because weight is this force that's due to this interaction known as gravity. We'll better understand that next week. We're going to do Newton's universal law of gravitation. Now, when I look at this formula here, I see an opportunity to make a graph. So what I want you to do is, in your notebook, I want you to make a graph of the force of gravity versus M, okay? So I want you to make a graph of force of gravity versus M. What kind of function would that be? So I'll give you 2 minutes to do that. So FG versus M. FG on the vertical axis, M on the horizontal. FG on the y-axis, M on the x. All right, and once you've made the graph, I want you to think about what the slope of that graph might represent. You're welcome. You're welcome. All right, so what kind of graph did you come up with? What would that function look like? So Shakira, what do you think? Well, we've got, what is our formula here? FG equals M times G. What if I wrote down Shakira, what kind of function is this? Y equals slope times X. Okay, it's a line. So, okay, Holly, which letter corresponds to our Y variable? Okay, so you have FG. Kayla, which variable corresponds to our X? Which variable up here matches up, goes with X? So we're doing a graph of FG versus M. Which variable would be the horizontal variable from FG, M, and G? What are we making a graph of? Remember, it's like Y versus X. So which letter corresponds to the horizontal? Not G, M. Okay.
That's what I said.
You know, it's messing me up because I'm thinking of slope as mx plus b. And that's why I'm all screwed up. That's why I wrote the word slope, so I wouldn't make that mistake, but I made it anyways. All right, so we've got FG versus M. What are we left with? Erica, what variable from the top are we left with? G. So what do you think G is, the slope or the intercept? Let's see, for it to be the intercept, it would have to be plus G. So, right, X goes with M here, and the slope would be G. I know it's weird. It's weird because you're used to like mx plus b. I get that. But what we're saying is, and I'll throw up the graph here, if I make a graph of the force of gravity versus mass, I get the straight line. What does it mean? What does it mean? Bless you. What does it mean about that the y-intercept is 0? Melissa, what do you think that means?
That the force of gravitation
Yeah.
is 0 and then mass is 0.
Yeah. That seems like it makes sense, right? If there's no mass, there should be no force of gravity. Okay, so the y-intercept part makes sense. What does, oh, I gotta get rid of this. What does the slope of this graph tell us? Well, we know it tells us, which letter again? Bless you. Int G, okay? According to this graph, what is the units of the slope? So, right, what would be the units of the slope here according to our x and y? So, Newton over kilograms. Okay? So it turns out that another way you could write G is you can say G is 9.81 newtons per kilogram. That's the same thing as meters per second squared, right? They're equivalent, but it's just another way to think of it. Bless you. This has a special name when you write it this way. It's called the gravitational field strength. I'll give you notes for that next week. But this is where the idea comes from. It says, for every kilogram, this is how many newtons you would get. If you've got 10 kilograms, bless you, if you have 2 kilograms, you'll get 20 newtons of force. 4 kilograms, 40 newtons of force. 6 kilograms, 60 newtons of force, right? Gravitational field strength. I'll give you notes about that next week because we're going to connect it to Newton's universal law of gravitation. But every once in a while, they like to ask it that, bless you. They like to ask you about it. They like to say, what's the gravitational field strength? It's just a fancy way to ask, what is G? Yeah, so what is a Newton equal to? A Newton is a kilogram meter per second squared. So if I divide it by a kilogram, meters per second squared is what I'm left with. It's really common to do this, to write these units that if you cancel them down, you'd get something else. All right, so I've got another thing for you to think about. I want you to draw the graph. Draw the graph that would represent this relationship, not on Earth, but on the moon. Okay? So on the moon, the acceleration due to gravity is 1.6 meters per second squared. Take a minute, draw the line on this graph that would represent that. All right? It's 1/6 our gravity, so it's 1.6 meters per second squared. What would that line look like? Would it be the exact same line? What about it would be less? The y-intercept, the slope? Draw what you mean. You can draw it right on the same graph. Still would be a straight line. It's still the same relationship of FG equals M times G. So the shape doesn't change. But what about the line would change? Think about how you can make a line different. How would it be lower? There's two ways it could be lower.
All right, so wait, so then there would be less weight, but the mass is the same.
So that would mean, yeah, if I had a 6 kilogram mass, it should have less weight on the moon than it does on the Earth.
Would it be like that, or would like?
Well, drawn relative to this line,
Yeah.
what would be different?
Would it be smaller?
Think it through. Pick a point and say what would
Maybe
happen.
smaller.
All right. So I think before I have you share with me the answer, let's talk first about the parts of the graph. So Vicky, should the y-intercept change? No, it should still be true that if we have no mass, we should still have no force, okay? Should the graph change its shape? Lauren, will our graph still be a straight line? Yeah, so it's not going to turn into a parabola or something else. It's still a linear relationship. All right, Natalie. Let's say I picked 6 kilograms. Should I have more weight, the same weight, or less weight on the moon than on the Earth? Less weight, all right? So in fact, if I sort of calculate it out, I should end up with what? About 9 newtons of weight. Okay, right? So it's 6. It's 1/6 the original. Okay. So what does this line look like? Orlandriana, what has changed about the line we're going to graph? And did it become more steep or less steep? Less steep. Okay. So the line, I made it more accurate. Let me do the orange one. Right? So that is the difference between gravity on the Earth and gravity on the moon, the steepness. What about if we went to Jupiter? What do you remember about the gravity on Jupiter? It's stronger, and where would the line move? It would become steeper, okay? It's a common question. I've seen it on 2 of the last 3 regions, and you have a homework question on it, where they'll give you the graph and ask you to come up with the slope, okay? You just figure out the slope any old normal way you would. I would definitely use 0, 0, because that's an easy point. Pick any of these other points, rise over run. You'll get the chance to practice that. I've seen it a bunch of times, okay? All right, so now we're gonna move on, and I would like to do a Plicker question. All right. All right, so. All right, so we've got. So a 65 kilogram astronaut weighs 638 newtons at the surface of the Earth. What is the mass of the astronaut at the surface of the moon, where the acceleration due to gravity is 1.62 meters per second squared? What would be, yep, there's your question there. So same thing, you rotate the card. When you've got your answer, hold it up, and I'll scan your card. Okay. Maybe you have to do math, maybe you don't, I don't know. If you need time to do the math. So you turn it to the answer you want. So if you want the answer C, you hold this side up, depending on what you hold up, okay? All right, who else still needs to, Lucero, I get yours? Yep, you can change your answer. Once I've got it, you can change your answer. Who else still needs, let's see, Lucero? Nadia, all right, so let's look at the graph here. So we've got a breakdown between, looks pretty much A and B. All right, so let's see. Shakira, talk to us about what you picked and why you picked it. There you go, right? So the mass stays the same, but the weight would change, right? So the answer is B. This is a good example of a question where the hardest part is knowing what they're looking for, right? I think those are hard because there's no calculation to do. You just have to know that the mass stays the same, okay? This question, and you'll probably see it either on the quiz or the test, is I'll also ask the follow-up, what about the weight? What would be the weight if we were on the moon?
No.
We would have to take, what would we do? We would multiply 1.62 and 65, and we would get 105, right? That's a good point too, right? So you can also work based off of the units. They're asking about mass, so it's gotta be A or B. It can't be C or D. All right, let's do the next one. All right, this one you'll have to do a calculation, but it won't be too tough. All right, on the surface of planet X, a body with a mass of 10 kilograms weighs 40 newtons. The magnitude of the acceleration due to gravity on the surface of planet X is, and there are your 4 choices. You will need to do a little bit of math, nothing too crazy, okay? We're still waiting for, let's see. Now that you got your answer? Almost? It's like I'm getting the glare. There we go. All right, who's still waiting for? Caitlin, you got your answer? Let's see. Lauren, you got your answer? I got it right. Oh, it's like I sort of have it, but I don't. You got it? Hold up yours. It's like blue, but doesn't have the check. Okay. All right. So let's see. Let's have. All right, Trinity, talk us through what you put and what you were thinking. Yes. Yeah. So this one I think a lot of people connected with, yes. And D is the right answer. I do want to talk for a second about sometimes it's good to be able to look at answer choices and know where they came from. Helps you kind of know what they were thinking when they came up with them. What about answer choice C? What's going on with answer choice C, Orlangiana? Right, this is what it would be on Earth, right? So they think you're gonna see 9.8 and go, oh, it's gotta be 9.8 because it's always 9.8. All right, what about with answer choice B? How do you think they came up with answer choice B, Crystal? Yeah, they multiplied it. They just assumed maybe you would make a mistake with the math. Instead of dividing, you would multiply. A, I'm not really, I mean, it's like double wrong. I don't know. You got an extra 10 somewhere, right? You didn't just do 10 times 40. You added an extra 10. Maybe you did, I actually have an idea. Maybe you did 10 times 40 times 9.8. you thought you had to multiply 3 numbers, not just 2. Sometimes it's helpful to put yourself in the shoes of the person that came up with the question, because you can cross out answers you know aren't true. So for example, as soon as I see on planet X, I go, oh, well, it's not going to be 9.8. We're not on the Earth anymore, right? So I've at least crossed out one answer, and hopefully I don't, or even if I have to go back and guess on this, now it's 1 out of 3 instead of 1 out of 4. Right? Always going to be a good strategy if you can use it. Right? So these kinds of questions will be they'll be in 2 homeworks because it's going to be combined with the universal gravitation stuff. Okay, so this one isn't the stuff that's on the next homework, but you will have a couple questions like this taken right off of the Reese exam. All right. The last thing I'm going to do is, we've got time, which is great. I want to go through how you would draw the free body diagram if you have something on a tilted surface. Oh, yeah. I should have put it in the Plickers. And I've got some nice, this is Planet X. Planet X. All right, so I was having a tough time on where I was going to kind of put this into the class setup. So we're going to do a lab that has to do with this as well. But I just want to kind of go over for a quick second on drawing this free body diagram. So this is the stuff that's on the next homework. So there's lots of videos and resources for you to watch, but I also want to just show you real quick. We can decide to draw a free body diagram any way that we want. And by that I mean, we can choose to put the coordinate system pointed in any direction that will make the problem easier. That's it's like a cool thing that you can do. It's also really hard to see why that might be useful. One place that it's useful though is when you take an object and you put it on a tilted surface. So this is called an inclined plane. We have ones that we're going to use in the lab in 2 weeks. And by changing the angle, I can change the forces that are acting on the object. Now the weight is always going to be pointed straight down. Okay, this blue vector doesn't change what direction it's pointed. But what will change is how much normal force there is. Okay, so to see that, let's go to the extreme. What if I tilted this so far over that it was straight up and down? And here is my box. What do you think the normal force would be in this situation? So we've got the weight is pointed down. What direction should the normal force point? Would it be up? Yeah, it's got to be to the side, right? It would be being pushed because the box is here and the wall would be pushing it to the left. But what would happen to this box if the normal force was like a number? How should this box move if the normal force is, let's say, 10 newtons? What would that force make the box do? Here I have a box. I will hold it up against the wall. How does this box move? Go straight down. If there was a normal force, that force should do, right? It should push it off the wall. If there was a normal force that was pushing the box, it should come off the wall. But that's not what happens. When I let go, it falls straight down. So what is the normal force equal to in this setup? 0. If we go to the other extreme, and I have the inclined plane completely flat, I still have weight pulling down. What direction is the normal force now? Up. It's pushing up on the box. And what is the normal force equal to? It's not 0 now, because if it was 0, the net force would point down and it would fall. What is the normal force equal to? It's equal in magnitude to the weight. So when the inclined plane is at 90 degrees, the normal force is 0. And when it's at 0 degrees, the normal force is equal to the weight, right? And Betsy, have you guys learned about the intermediate value theorem yet in calculus? So if I have a function, if I'm at 0 degrees, it's a positive number, right? And at 90 degrees, it's 0. Well, then there must be some function that goes in between that hits every value in between them, okay? Basically, the point I'm trying to make is the normal force goes from being 0 to being a maximum, and it'll do every number in between. There's a function that will tell us that, okay? So that free body diagram will help you figure out that function. Mr. Sample? Good, Ari. Oh, okay. Yep. All right, bye. All right, so to figure out the normal force, we've got to take the weight and break it up into a component that points opposite the normal force and a component that points down the inclined plane. This component you might call the parallel component, and this you might call the perpendicular component. We've broken up vectors into components before. The tricky part, and we can do some geometry to show it, is figuring out where the angle is located. So I'm going to draw this triangle here, okay? This angle here is the angle theta. This angle must be 90 minus theta. Because all the angles in a triangle add up 180. This is a right triangle. This is theta. This is 90 minus theta. There's another right angle here. Because this line is perpendicular to the surface. So let's see, if this is 90 minus theta, and this whole thing is equal to 90, then this side is equal to theta. Just a geometry thing. The first time I saw this, I just didn't believe it. I said, that doesn't make any sense to me. But once you follow, it's just it's a triangle and then a 90-degree angle. But what's important is that the angle theta is located not between the weight and the parallel, it's between the weight and the perpendicular. Theta goes here, not here, here. So now if I want to use sine and cosine, let's see, the parallel piece would be this part of the triangle. That is is it the opposite side or the adjacent side? Here is our angle. Here is the side. It's opposite. So this is equal to the weight times the sine of the angle. Okay? And the other piece is equal to the weight times the cosine. So that means on an inclined plane, the normal force is equal to the weight times the cosine, and the parallel part, or sort of the gravity that's parallel, force of gravity pulling it down the incline, is equal to the weight times the sine. They love to ask this question about this, and I feel like it's not really fair. I think being able to do this drawing is really hard. I totally think that. If you're looking at this and you're still really unsure about it, we'll get you there. But I want you to know that this was a hard thing for me to do when I was first learning it. So my goal doesn't make me happy to say, but in reality, at the end of the day, I want you to have that memorized. If you can do the diagram, that's great. That's awesome. That's the big goal. But I want you to know that if all that ends up happening is you memorize these two things, that's okay too. Okay? Because the kinds of questions they ask is they just want to know what is the normal force. That's what they'll ask. Or they'll ask it as parallel and perpendicular. You'll see both versions of that on the next homework. Okay? I was really struggling with how I was going to get this into our class. I think this is just the best way to do it. I look forward to your feedback about it, but know that it's a tough thing to do, and I totally get that. Lots of people will switch this, they'll mess up this angle, but what can be helpful is to think about the two extremes. What should the normal force be if it's perfectly flat, and what should the normal force be if it's up and down? And if you know that, if it goes from a maximum to a minimum, that's exactly what the cosine function does. The cosine function starts at 1, and then it becomes 0 at 90 degrees, right? So that might be another way to help you remember what's going on here. Whatever strategy works best for you is the one that you should do. So tomorrow we have a lab. Please take an opportunity to read through the lab before you come to class. It's posted on Google Classroom. That'll just make lab go a little bit smoother. It's going to be upstairs on the 9th floor. Okay? So I'll send you a message to remind you to go. I'll send you a remind to remind you to go there. You don't have to bring your workbooks. I'll have your lab notebooks up there for you to fill out. Okay? One sec.